Okay, so can you see this excess properties?
Yes, sir.
Yes, sir.
Okay. So we have seen so far what have we done? So क्या क्या किया हमने अभी तक यूनिट 2 में? टॉपिक्स याद है किसी को? नहीं याद है. Okay, so we have seen volume change on mixing, enthalpy change on mixing, Gibbs change on mixing, सब देखा, right? Now we'll look at excess properties because that will help us define activity coefficient. We have introduced a term for activity coefficient, and what does activity coefficient represent? Why did we introduce activity coefficient? Can someone tell me activity coefficient क्या represent करता है? Can you hear me?
Yes, sir.
What does activity coefficient represent? How was it introduced?
Deviations from the ideal one.
Yes, so it is essentially what we said is कि Raoult's law बोलो या Lewis Randall rule बोलो, that is applicable for ideal solutions. So if you want to account for non-ideality or real solutions, then we have to introduce a term called activity coefficient, which will tell us how much is the deviation from the ideal solution concept. ठीक है? Now we are going to go one step further and talk about excess properties. तो रेसिडुअल प्रॉपर्टीज आपने देखा थर्मो 1 में. Have you seen रेसिडुअल प्रॉपर्टीज इन थर्मो 1? किया था क्या? नहीं हुआ था. Okay, so residual property is defined for pure fluids, which is should be part of thermo 1. इसलिए मैंने थोड़ा यहाँ कवर किया है so that you understand the concept. And H superscript S R is enthalpy, residual enthalpy, is equal to H minus H ideal, where H is the enthalpy or real solution or real fluid, pure fluid. So we are talking about pure fluid. So if we started with ideal gases, right? And then we introduced some equations for non-ideal gases, Peng-Robinson, etc., etc. So residual property was defined as deviation between real gas property and ideal gas property. So H is equal to H minus H ideal, or sorry, H superscript R, residual property, and S is entropy, residual, is equal to S minus S ideal. So it is nothing but enthalpy, thermodynamic property at any temperature and pressure minus property of ideal gas at the same temperature and pressure. Right? So it will tell us how much is the deviation between real and ideal fluid. Okay? So now is along the same lines introduce excess property for solutions. That was for pure fluids. Residual property was for pure fluids. Now excess property is for solutions. So we define any property M superscript T is excess property as property of a real solution minus property of ideal solution. Okay? So previous one residual property was for pure fluids. Now this is for solutions. Okay? And this is nothing but difference between actual property or real property of a real solution and property calculated for the same temperature and pressure and composition, because it is solution now, by equations of ideal solution. So difference between real minus ideal. So M superscript T is nothing but M minus M ideal, similar to if you see HR was for pure fluids, S minus S ideal or H minus H ideal. Similarly, M superscript T is any definition of excess property. Okay, there are no questions. Then we define excess property change of mixing. Right? Delta M superscript T. So when you mix two solutions, what is the change property change of mixing, that is called excess property change of mixing. Mixing कर रहे हैं दो solution, तो क्या change होगा? So delta ME, the change in property or excess property when you mix two solutions to make a third solution, right? So delta M, it is for real solutions minus delta M ideal. Along this equation 1, different and ideal. ठीक है? Any questions? Okay. So delta M property change किया था, delta G, delta H, delta S for real solutions, right? And then for ideal also हमने देखा था कैसे simplify हो जाता है वो, right? And delta M ideal is property change of mixing of ideal solution. So we're talking about difference between real and ideal solutions now, excess property. ठीक है? Any questions? Okay. So we have defined delta M by this equation. Delta M is equal to M minus summation of xi mi0. Mi0 is for pure fluids. And for ideal it was M ideal minus summation of xi mi0. Okay. So if you take delta ME by definition, delta ME is nothing but this minus this. We define this and this. So we substitute in this one and we get M minus summation of xi mi0 minus M ideal summation of xi mi0 minus superscript 0. So delta ME is nothing but M minus M ideal. ये दोनों cancel हो जाएगा. This and this cancel out, and what we get is M minus M ideal. ठीक है? So if we compare 1 and 3, 1 was excess property is equal to M minus M ideal, and 3 is delta ME of mixing is equal to M minus M ideal. So if you compare these two, left hand side is same, or right hand side is same, so left hand side has to be equal. So delta ME is nothing but ME. So excess property of mixing is nothing but excess property by definition. So excess property change of mixing is nothing but excess property. Any doubts, questions?
सर इसका मतलब नहीं समझा।
मतलब क्या समझने का, डिफाइन कर रहे हैं हम ये क्या होता है।
हाँ तो डेल्टा एमई और एमई में डिफरेंस क्या है?
क्या बोला था डेल्टा एमई?
प्रॉपर्टी चेंज ऑफ
एक्सेस प्रॉपर्टी चेंज ऑफ मिक्सिंग, मिक्स टू सॉल्यूशंस, तो क्या होता है प्रॉपर्टी चेंज ऑफ मिक्सिंग? हमने देखा लास्ट टाइम। व्हाट इज प्रॉपर्टी चेंज ऑफ मिक्सिंग देखा था हमने। फॉर आइडियल सॉल्यूशंस देयर इज नो वॉल्यूम चेंज ऑन मिक्सिंग, राइट? इफ आई मिक्स टू आइडियल प्योर फ्लूइड्स and make a solution, there is no volume change on mixing for ideal solutions, right? Non ideal में क्या होता है हमने define किया था बाद में, right? For volume, for enthalpy, for free energy, for entropy, सब किया था हमने। Now we are saying कि अगर हमने real solution उसके लिए property जो हमने लास्ट टाइम डिफाइन की, व्हाट वी डिफाइन लास्ट टाइम, राइट? दिस इज द प्रॉपर्टी चेंज ऑफ मिक्सिंग फॉर रियल सॉल्यूशन, जो हमने डेरिवेशन किया था V के लिए, H के लिए, N, G के लिए, सब के लिए। नाउ इफ यू टेक डिफरेंस ऑफ दिस रियल माइनस आइडियल के लिए क्या होता है, दैट इज योर डेल्टा ME, एक्सेस प्रॉपर्टी चेंज ऑफ मिक्सिंग।
यस सर।
It is the difference between real minus ideal. Always we are talking about real minus ideal, because we always take ideal as a base, because we can easily calculate or evaluate ideal solutions, whereas it's difficult to evaluate for real solutions. We always say कि कितना difference होगा इससे, real का कितना difference होगा ideal से, and that's how we always approach it. whether we take ideal gases and real gases, ideal solutions, real solutions. Now we talk about excess property में भी वही से कर रहे हैं, real minus ideal. ठीक है? So now we are just proved
Yes,
that delta m is nothing but me by definition. जो हमने डिफाइन किया था ऊपर, excess property is nothing but delta me. यानी property change of mixing, excess property change of mixing, this me, this one is nothing but what we define here. ये वाला. So these two are actually same. That's what we define. Proved, rather proved. Okay. Now we'll use this concept to our actually find out activity coefficient कैसे निकालना है. Ultimately objective is to find out activity coefficient. हमने ये concept introduce तो कर दिया कि activity coefficient डालेंगे to account for non-ideality. But how do we actually calculate it? This is a difficulty. So we have to somehow calculate it, and that's how we are going to approach this through excess properties. Right? So if you use this delta me is equal to me, by that thing V excess is equal to delta V excess, right? Volume change बोला तो. That is equal to nothing but delta V minus delta V ideal. This is by definition. Given by definition. Right? Delta V excess is nothing but delta V for real solution minus delta V for ideal solution. Right? And we know that for ideal solutions there is no volume change of mixing. So delta V ideal is equal to 0 for ideal solutions. Right? So if we put it here, what we'll get is V excess is nothing but delta V. So excess volume is nothing but volume change of mixing. In the case of volume, not for other thing. We'll see that. In some cases it will be same, in some cases it will be different. Right? Similarly, we can say that H excess लिया by this definition, ये जो लिया H excess ये लिया हमने. Suppose we define H excess like this, right? H excess is equal to delta V excess is equal to delta H minus delta H ideal, right? And we know that delta H ideal is equal to 0. हमने prove किया था last week. So H excess is nothing but delta H. Right? And similarly, U excess nothing but delta U, because delta U ideal is equal to 0. Why is delta U ideal equal to 0? Why is this equal to 0? हमने प्रूव नहीं किया था ये, but I am saying this is 0. So if you see, delta H क्या होता है? What is delta H equal to? Delta U plus
V.
plus PdV, right? P delta V. बराबर है? If I put ideal here, ideal here, ideal here, right? So delta is equal to delta U ideal plus P delta V. P delta V ideal हमने 0 प्रूव किया अभी. And delta H ideal is equal to 0. So delta U ideal is equal to 0. ठीक है? This is equal to 0. This is equal to 0. This is equal to 0. ठीक है? Any questions on this? So delta U ideal is equal to 0, delta H ideal is equal to 0, and delta V ideal is equal to 0. right? ये प्रूव किया हमने. But when it comes to free energy, हमने पहले देखा था, right? Last week हमने प्रूव किया था delta G for real solution is not equal to 0. It is something, right? Delta G for real solution was something, or delta G for ideal solution was RT summation of xi ln xi. ये हमने प्रूव किया था last time, right? And since xi is not equal to 0, so this is not equal to 0. And we have also proved delta S ideal is equal to minus R summation xi and xi. And since xi is not equal to 0, this delta S ideal is not equal to 0. Right? So we can write gxs is equal to delta gxs is equal to delta g minus delta g ideal. Right? And S is equal to delta S x is equal to delta S minus delta S ideal. Right? But this term is not equal to 0, delta g, right? And delta S is also not equal to 0. Therefore, delta g xs is not equal to delta g. Okay? So g xs is not going to be equal to delta g, and s x is not going to be equal to delta s. There are only two cases in which there is these two access functions and properties of mixing are not equal. Any doubts, questions on this? Okay, there are no questions. That means we have introduced two new terms, new functions, g axis and entropy axis. They are new terms, new functions which we have introduced, defined now. Okay, so now we'll see access functions essentially define deviations from ideal solution behavior. हमने देखा था, right? We define access function is deviation from ideal solution behavior, and access function can be positive or negative. We'll see that. So access gives free energy can be a positive or negative, indicates, and this indicates positive or negative deviations from ideality. We'll see later on how it is used. Okay, so now let us see how we can use this access property to define activity coefficient. Ultimate objective is that only. How do we get activity coefficient? Any questions or doubts so far? Gxs, that's what we are going to use. Excess molar Gibbs free energy. कुछ डाउट है, क्वेश्चन है किसी को?
No, sir.
Okay, so let us see, go back to partial molar properties definition. Mi bar is equal to daba nm, that is m total, this is m total. This is total property, right? M into n into m, because m is molar property. So if there are n moles, then n into m is total molar property, divided by daba ni at constant temperature pressure n, where j is not equal to I. And that's what we have done, right? Instead of this, now we have written mt daba mt by daba ni at constant temperature pressure and nj, where j is not equal to I. So if we take partial molar excess property mi bar e, similarly we can define that, right? Just like we defined other properties, we can define excess property for partial molar excess property. Mi bar e is equal to nothing but n into me, molar excess property, by daba ni at constant temperature pressure and ni, nj, and the j is not equal to I, right? And we also defined m is nothing but total molar property is summation of xi into partial molar property, mi bar. Similarly, we can define mxs is equal to summation of xi mi bar e. So partial molar excess property, mi bar e is nothing but partial molar excess property. So me is equal to molar excess property, which is nothing but average of partial molar. So this is this one. Molar excess property is nothing but average of partial molar excess property of each component weighted by mole fraction. That is what this is, summation of xi mi bar e. So now we can relate excess property to partial molar excess property. ठीक है, questions? Okay. And then we introduce another term called excess Gibbs free energy. Right. Similarly, we use excess Gibbs free energy, and this is used for phase equilibrium. This is what we'll be using throughout for phase equilibrium. Right. So G excess is defined as G or Gibbs free energy for real solution minus Gibbs free energy for ideal solution. Okay. And we also know that ME is equal to summation of Xi Mi bar E. So G excess, you can say, is summation of Xi Gi bar E. And we know that partial molar excess Gibbs free energy is nothing but mu I. So it is mu I E. Partial molar excess Gibbs free energy of component I. So mu I bar E is excess chemical potential or excess partial molar free energy. Okay, any questions on equation 12? Okay, so then we say mu I E similar to Ge is equal to mu for ideal solution minus mu I for ideal solution is equal to, we have proved this, right? Mu I is equal to delta mu I minus delta mu I ideal. Because we proved delta mu I is equal to mu I. The delta mu I is change in chemical potential of I when it goes from standard state to solution at the same temperature and pressure. So mu I is excess partial molar free energy for component I. Right? And we have defined what d mu I is equal to RT dln Fi bar. So if we integrate from Fi0 to Fi bar, what we get is delta mu I or d mu I from mu I 0 to mu I ideal state, standard state to mu I is equal to RT dln Fi bar from standard state Fi0 to Fi bar. And this will give us delta mu I is equal to RT ln Fi bar by Fi0. This we have seen before. Nothing new here. पहले भी किया हमने, right? Where Fi bar is viscosity of I in solution and Fi0 is viscosity of I in standard state. Similarly, if the component is part of an ideal solution, delta mu I ideal will be nothing but RT ln Fi bar ideal by Fi0. Instead of real solution, it will be ideal solution. Similar to equation 14. Okay, and we also define viscosity of ideal solution is equal to Fi ideal, Fi bar ideal is equal to Xi Fi0, which is nothing but loose Randall rule. Therefore, we can say this equation will become this equation. Delta mu I ideal is equal to RT Fi ideal, Fi bar ideal by Fi0 is nothing but ln Xi, or sorry, Xi. So delta mu I ideal is RT ln Xi. Any questions on equation 16? Similarly, we have defined for non-ideal solution Fi bar is equal to gamma I, where gamma I is nothing but our activity coefficient. Ultimately, we want this one into Xi Fi0. So substitute this 17 and 14 in equation 17 and 14, right? So if you put 17 and 14, here what we'll get is delta mu I is equal to RT ln gamma Xi. Like we had this Xi for ideal solution, we have gamma Xi for non-ideal solution. Okay? So now we substitute 16 and 18 this equation for mu I ideal and delta mu I for real solution in 13. 13 is mu I excess is equal to delta mu I minus delta mu I ideal, and what we'll get is mu I excess is equal to delta mu I minus delta mu I ideal is equal to RT ln gamma xi minus RT ln xi. Ln xi will cancel out, and what you get is mu x is equal to RT ln gamma I. So now we have an equation which shows what is the relation of partial molar excess free energy with activity coefficient, which is equation 19. ठीक है? Any questions on equation 19? Okay, so substitute equation 19 and 20. 20 is what? Gx is nothing but summation of xi gi bar e, or is equal to summation of xi mu I e. And what you get is gxs is equal to RT summation of xi. We substitute here summation of xi into ln gamma I. Where mu I is nothing but gi bar e, partial molar excess free energy of I in solution. So from here, equation 19, what you get is ln gamma I is equal to mu I e upon RT. If you take RT here on this side. And what is mu I e? It's nothing but partial molar excess free energy. So it is double NGE by RT by double Ni at constant temperature pressure Nj, where J is not equal to I. And this is by definition Mi bar E is equal to double N into Me by double Ni at constant temperature pressure Nj not equal to I. So this is what we are going to use now for our derivations. Relation between mu I e and ln gamma. Any questions on equation 22? Yes, no, कुछ समझ रहा है कि नहीं समझ रहा है?
हाँ सर समझ रहे.
Yes, sir.
Okay, so let us move further. Now we are going to see how we apply this equation 22 for actually finding out ln gamma. So this one Margulis equation कभी सुना आप लोगों ने? नहीं सुना? ठीक है. So this equation is Gxs is equal to Ax1 into x2, where x1 and x2 are mole fractions of component 1 and 2 for a binary system. So if you take ln gamma I, this equation is equal to mu I e is equal to double ln n g by RT by double ni at constant temperature pressure and Nj. For a binary system, we can write this equation as ln gamma 1 is equal to double n g by RT by double n1 at constant temperature pressure N2, and ln gamma 2 is equal to double n g by RT by double n2 at constant temperature pressure and N1. Right? So if you take this equation, G is equal to Ax1, x2, and write x1. x1 is nothing but N1, number of moles of 1, divided by total number of moles, and x2 is N2, number of moles of 2, divided by total number of moles. So if you take 1n here, you get n into G is equal to A into N1 N2 upon N, because we want this one, right? We want this term, Ng. So we are taking 1 and G here, N here on the left hand side, and we divide by RT. So Ng by RT is equal to A by RT N1 N2 upon N, because we want to take this partial derivative, right?
सर अपोनेंट नहीं आएगा ना? नहीं सर बराबर है.
Sorry, disconnect हो गया था वो. I am back again. Recording चालू है. Okay. So now we want to take partial derivative of this Ng by RT. So what we get is n is nothing but n1 plus n2 for binary system. To differentiate equation 25 with respect to n1, keeping n2 equal to constant. So what we get is double ng by rt double n1 at constant n2 is equal to a by rt into double n1 n2 by n. Right? So if we take n2 equal to constant outside, it is a n2 by rt double n1 upon n is nothing but n1 plus n2. Okay? So if we take this n1 upon n1 plus n2, it is nothing but d of u by v. It is the denominator into derivative of numerator minus numerator derivative denominator by denominator square. So we take that here, a n2 by rt, denominator is n into derivative of n1 with respect to n1 is 1 minus n1 is numerator into denominator is again 1 by n square. So n1 cancels out, and what we get is a n2 square upon rt n square. This is equal to a by rt into n2 by n is x2 square. So we get equation 26. There is a derivative, partial derivative of nge by rt. So if you compare equation 23(1), this one, with 26, right? This is right hand side. This right hand side of equation 23-1, and this left hand side is same. So what we get is ln gamma 1 is equal to a x2 square by rt. So ultimately are substituting for that partial derivative. Okay? And similarly, we can get ln gamma 2 is equal to a by rt into x1 square. So now we have equation to calculate activity coefficient gamma 1 and gamma 2 if you know the constant a for Margulis equation, and that we'll see how to find out the constant a for Margulis equation. Okay? Any questions, doubts? इक्वेशन 28 पर 27 पर किसी डाउट है क्या? समझ में आ रहा है?
Yes, sir.
Yes, sir.
Okay. So now we have, see, ultimately what we did is we defined ideal solution, then introduce a factor for non-ideality, which is gamma 1. Now we are going to calculate gamma 1 or gamma 2 or gamma I using all these equations. We'll see later on other equations are also available. Van Laar equation is there. There are other equations. Wilson equation is there. There are many equations which can be used to find the activity coefficient, and then we can have equation for non-ideal or real solutions. Okay, I'll be sharing this thing with you, notes वगैरह. You'll have all these notes. ये एग्जाम में आता है, एग्जाम में जनरली कभी कभी आता है, not always. Like this is 2017. Excess enthalpy of our solution is given by H excess is equal to x1 x2 into 40 x1 plus 20 x2. Derive expressions for h1 bar e and h2 bar e as functions of x1. We'll see that next time कैसे derive करते हैं. I'll show you next time. ठीक है? But go back home and read something. Read the notes. Book में भी अच्छा दिया है, so that your ideas are fixed. If you have any doubts, you can always come back and ask. So any questions on what we did today? So next week on Monday, we'll have a test at 2:45. No lecture will be there on Monday. From now onwards, only test will be there on Monday. ठीक है?
Yes, sir.
Okay, then I'll stop the recording and end the meeting.